All right. Well, thank you so much for the invitation. All the best in these times. So this talk is based on, well, there's really three papers that I'll be summarizing some results from. The first of which was from last June, and then a couple more recently. All of them were co-authored with Jordan Cutler, who's a fantastic postdoc at Harvard now. And I'm going to try to simulate a Blackboard talk as best as I can in this. We'll see how successful that is. If you have any questions along the way, of course, please feel free to speak up. Hopefully this will be a nice interactive discussion. So where we start in this talk is with black holes, which have long been known to be thermodynamic objects. We've known this since the 70s with all of the revolutionary papers of Hawking and Page and others on black hole thermodynamics. So they're thermodynamic objects with, an energy, a temperature, an entropy, etc. And from the beginning, there was a question with black holes: to what extent do black holes, do these thermodynamics, does it have a statistical mechanical interpretation? So there was black hole, in the beginning there was black hole thermodynamics, but is there black hole statistical mechanics? And this question was impossible to address in classical general relativity. In classical GR, the entropy of a black hole goes like 1 over g Newton, where g Newton is very, very small. So the entropy is non-perturbatively large in g Newton. And correspondingly, the sort of level spacing that you might expect between between different microstates that would make up the black hole, well, that level spacing, you would just, if you wrote it down, you would expect it to be of order e to the minus 1 over g Newton. And just non-perturbatively small and impossible to resolve in classical gravity. So what one has instead from classical gravity is a coarse-grained approximation to the density of states. And that coarse-grained approximation is continuous. You don't actually see it resolve into a bunch of delta function spikes, which you might hope is what actually constitutes the spectrum of states of a black hole. Now, famously, in string theory, there are instances where we can really say, where we know that there are black hole microstates. The black holes, their thermodynamics can be accounted for in terms of microstate counting, and we can enumerate what the microstates are. I have in mind Strominger-Vafa in particular. And we can describe them. So in that case, you consider some supersymmetric black holes that are built out of d-brane intersections, and you can really count the microstates in terms of states on the world volume theory of those d-branes. These black holes are supersymmetric, and these states are BPS and so on, but at least you can count them. At least it's something. Makes up the black hole. So that, there's good reason from string theory to think that there really is some statistical mechanical description of black holes, at least in an ultraviolet complete theory of quantum gravity, and that the states can be counted and so on. Let's fast forward a little bit. In AdS CFT, this question of black hole microstates takes on a more refined meaning. Oh. Okay, so in AdS CFT, the problem of black holes in AdS, so a black hole in AdS is dual to a thermal state of a dual conformal field theory. And for instance, if we consider black holes in global AdS, well, those are dual to very, very heavy states in the dual CFT. So the black hole microstates in that case are dual to very heavy states in, well, the dual CFT. And well, the precise details of that microstate spectrum are, at least in the present day, in the year 2021, they are out of our reach. They're inaccessible with current techniques for generic black holes in AdS. So the exact details of the spectrum are unknown. The energies and the quantum numbers of those microstates. But what we have is from coarse-grained, from Einstein gravity, or the supergravity regime, if we're talking about something like AdS 5 times S5, well, we have black hole thermodynamics again, and that gives us a coarse-grained approximation to the density of states. And the picture that you end up with is something like this, say for n equals 4, AdS 5 times S5. The picture that one gets for the density of states is as follows. So what you get from gravity, you get very, very light states. So see a Dirac comb of light states with energies of order 1, say order root lambda, with lambda the 't Hooft coupling, order n, dual respectively to fluctuations of supergravity modes, fundamental strings in AdS, and branes, d-branes. And then off at, objects in AdS, and then at energies of order n squared, you get new states. You get a continuous spectrum, and those are the black hole microstates. And in the supergravity approximation, you get a continuous density of states. Of course, what we actually expect that happens in real n equals 4, in non-perturbatively in 1 over n, is that this continuous bath of black hole density of states in the black hole regime, that it's resolved into a very, very fine Dirac comb with a bazillion delta function spikes, just with an extraordinarily small level spacing.
Sorry. What is n? What is n?
Hang on just a second.
Number of brane?
Yes, yeah. So I have in mind for, say, AdS 5 times S5 with n units of 5-form flux, dual to n equals 4 with gauge group SUN. So n being the number of 3 branes.
Okay. Thank you very much.
And the dictionary in that case has G Newton, or 1 over G Newton, roughly of order n squared. So the level spacing will be non-perturbatively small and large n. And we know a lot for n equals 4 about the light part of the spectrum. Super conformal symmetry helps us a lot. Those states are, well, certainly the states with order 1 energies are protected. And those of order lambda, order n energies are, there's fewer constraints on those, but there's still quite a bit of information that we have about those states coming from the maximal supersymmetry. But it's worth noting that in the black hole regime, that's generic, that's really the unprotected part of the spectrum. That's the complicated part. And so, okay, so we get from gravity some coarse-grained approximation to that very, very fine Dirac cone. We get a coarse-grained density of states. It's an interesting function. One might wonder if there's further information that we can get out of the microstate spectrum from bulk effective field theory. So can we learn more? And the question that I want to focus on today is not so much the density of states itself, which, okay, maybe that could be a future thing to discuss. What I want to talk about is a more refined observable that is, is more commonly discussed in condensed matter physics, namely the level statistics of those black hole microstates. And what do I mean by level statistics? Well, what I mean is, the set of energy eigenvalues of n equals 4 on a sphere, or equivalently the set of energies of black hole microstates, it forms some set. Maybe energy of the first state, energy of the second state, energy of the third state, etc. There's infinitely many of them, evidently. And those energies, if you order them, and then, so you have first state, next state, and so on, and then consider the energy differences. And then you order the set of energy differences. So call that delta 1, delta 2, delta 3, from smallest to biggest. Those are the level spacings between energy eigenstates. And those level spacings, there's, you might think that they're just, some complicated thing, that there's very little universal or robust information about those. However, there are expectations from condensed matter physics that that is not the case. That for a generic, complicated many-body Hamiltonian, so a chaotic Hamiltonian, there's an expectation that these energy level differences have certain universal features. So for instance, if you take those differences and there's a set of numbers there, and if you coarse grain a little bit, you bin them by a little bit, you get some new distribution of energy level nearest neighbor energy level differences. Let's call that distribution rho tilde. Well, for a generic chaotic Hamiltonian, this nearest neighbor distribution has a universal scaling near 0 level spacing. Oh, I had my hand on the eraser instead. That is easy to fix. It goes like, it goes as order energy level spacing squared. In particular, it goes to 0 as the energy level spacing goes to 0. And this phenomenon, this is called nearest neighbor repulsion, or eigenvalue repulsion. It's the thing that in a quantum mechanics class, there's something that you inevitably do is to study how to say 2x2 Hamiltonians when you talk about perturbation theory. And you notice that when a 2x2 Hamiltonian, as you adjust the parameters, that it takes an exceptional amount of fine tuning to make the energy levels degenerate. They usually want to be non-degenerate. This is the many body version of that statement. In a generic Hamiltonian, the energy levels want to be different. They want to repel. And there's some scaling that's universal for many systems. Depends actually on the symmetry class of the Hamiltonian. That's one thing that you might expect to get from gravity. However, this level spacing, if we're talking about.
Question? Sorry.
Yeah, go ahead, Subrat.
Yeah. Sorry. Yeah. The question is this dimension dependent, or is this a dimension independent answer?
So the statement coming from the condensed matter physicist is that this is true for a generic many-body chaotic Hamiltonian.
I see. So it doesn't care about the dimension.
Yes, that's right.
Sorry, Kristan, isn't this for quantum mechanics? You know, like, are we supposed to think about this even for, you know, like extended systems, you know, where there is a, you know, like.
Yeah, I mean, I can think of a lattice gauge theory as a particularly complicated quantum mechanics.
Yeah, lattice gauge theory with some IR cutoff.
Yeah, that's right. So for example, lattice gauge theory on a sphere.
Right. Yeah. You know, like something like that. So isn't that necessary? I mean, like, do we expect this to hold even if, you know, like we take this? I mean, what I'm asking is that doesn't this basically ignore the IR effects? You know, like, I mean, this is an expectation ignoring that IR is not a problem.
That's right. That's right.
That you can just do something at IR, and, you know, like that, assuming that doesn't change anything much, you know, you're kind of in the, you know.
Yeah, the way that I think about this is simply, you know, this is some kind of theoretical prior that was new to me to learn, and one can go ahead and start trying to assess it in theories that, well, in string theory or in n=4 or some such, and see whether or not it holds.
Okay. Yeah. I mean that's why it's dimension independent, right? Because in some sense it's kind of, you know, like it doesn't depend on IR, you know, like I would say. All right.
Yes, that is. I think that's one way of saying it. I mean, if you.
I mean, if I may just rephrase it, I mean, this happens in systems where there are no phase transitions, finite volume systems, quantum mechanical systems, you know, like, you know, where you have your kind of.
Yeah, since you're in finite volume, yeah, if finite volume, finite n, you won't have phase transitions.
Yeah. So I think that's probably the way to think about it. That this is an expectation when there are no phase transitions, or if somehow you think that the phase transitions are not relevant for this physics of this energy spacing, then maybe you expect something like this.
I think I agree with that statement.
I was thinking there's also an issue. Sorry. I was thinking there's also an issue of conformal symmetry. If you had conformal symmetry, you could, you know, you would say that you put the theory in a finite volume, and then you would know how the entropy scales. It would have to scale like Vt to the d in these spatial dimensions, and that would give you some estimate for the density of states, and that seems to be dimension dependent. That's why I was asking. Because if you're going to consider CFTs, there would be a dimension dependent answer here.
The precise form of the density of states, of course, depends on the dimension. If you consider, high temperature conformal field theory, then indeed their density of states has an approximately universal form at very high energies coming from the conformal symmetry. But I'm trying to distinguish the density of states from the level statistics.
So how can they be distinct? Isn't the level statistics related? If there's energy gaps are small, doesn't that also control the density of states?
When we talk about the density of states, we're really talking about coarse-grained approximation to it.
Right. That's
which is insensitive to the details of the level spacings.
Yeah, that I agree. But if you integrate the level spacings up to some number, you would get the number of states below some energy. So they can't be totally independent, can they?
They're not. However, how to say, I mean, it's that sure, you can ask how to say if you cook up a beer, how to say. However, if you have, I think what I'm trying to say is that if you have a very, very fine cone, a very, very small level spacing, and you coarse grain over order 1 amounts, then for many, many different patterns of level spacings, you can get the same density of states.
Okay. Okay.
Just knowing the coarse grain density of states doesn't give you that much information about the level spacings. It gives you some constraints. I'm not saying there's no relation. It's.
Okay.
What I was going to say about this is that the nearest neighbor repulsion. Oh, let me just. There was one thing I just wanted to say, and then I'll, and let's talk about this. So this information is probably far too fine-grained to access in gravity, even in terms of a sum over topologies, because this levels, the sort of extreme version of this, the smallest level spacing between the smallest level spacing between adjacent levels, is again of order, I keep writing this down, e to the -1/g Newton, or e to the -n², which is way too small. As a result, there's something that builds up that's a consequence ultimately of nearest neighbor repulsion, which is called long range repulsion. Roughly speaking, it's the statement you can think of the energy eigenvalues as kind of like repulsive elements in a gas. And if you have energy eigenvalue here, well, it repels against the next one, and that repels against the next one, and you build up a chain. So even if you have energy eigenvalues that are separated, that are not nearest neighbor, but are far away along the chain, well, they still repel. There's long range repulsion that follows from the short range repulsion. And that long range repulsion, there's some expectation that if we call that second moment of density of states, depending on two energies, that goes as a minus sign. That's the repulsion. If you were dealing with a finite dimensional Hilbert space, then dimension squared, E1 minus E2 squared, for energies that are order 1 apart from each other. So much further apart than the level spacing, but still not, very large energies. And what I'm going to focus on in this talk is I say I'm going to present some evidence that this is encoded, this long-range repulsion, not necessarily this quantitative form, but the qualitative feature of long-range repulsion is encoded in Euclidean wormholes in AdS. Tarka, sorry, I rudely stopped you, right?
No.
Go ahead.
Sure. I just wanted to clarify, means for the level statistics in context of CFTs, are you just looking at the spectrum of the primaries, or? Yes.
Crucially, spectrum of prime. Yeah.
Yeah, and is it also within some range, above some gap, or do you have to also specify your sample, where you are sampling the primaries from?
Right. So, how to say, the sort of the short range and the long range repulsion in a generic system, that those are effects that are robust and generic when you are some distance away from the spectral edge. Doesn't have to be very far, but you have to be a little bit away from the spectral edge.
Okay, and means it need not be exactly at the center, or
No, you don't have to be exactly at the center. Just basically, what you need is for the density of states there to be large. So if you're very close to the spectral edge where the density of states is becoming small, then you have to be more careful. But when the density of states is quite large, then these are fairly robust.
I see. Okay. Thanks.
Okay. So a comment that I want to make too, this long range repulsion and the short range repulsion, these things can be accessed another way rather than looking at sort of 2-point functions of density of states. There's another way to see them, which is in terms of the so-called spectral form factor. What this is, you can think of it as a second moment of the partition function. And second moment, well, what if you consider an ensemble of Hamiltonians, or if you consider a single Hamiltonian, either way. Consider trace e to the minus beta h plus I ht, trace e to the minus beta h minus I ht. So if we just had beta, this would be thermal partition function. And if we just had big T, then this would be the time evolution operator, say for CFT on a sphere, some complicated quantum mechanical system. Then if you plot this for generic complicated Hamiltonian, you get some, this is, you know, I'm not putting down references here. There's a ton of references for this that we included in our papers. What you get for this, let's call this thing Z of beta T. What you find is that it has some behavior on a log-log plot that looks something like, okay, well, that's not quite what you get. What you actually get is something like this. You get something with an enormous amount of oscillations. Some very complicated, very complicated thing once the time is of order e to the n squared, maybe times, you know, but you know, maybe divided by a factor of 100 or something. But before that point, you get a fairly smooth curve. After that point, you get a wildly oscillating curve. However, if you do one of either two things, if you either take a small time average with a single instance, or if you ensemble average over Hamiltonians that are very close to the one that you're studying, then in either of those cases, you end up getting this black curve, this thing that's fairly smooth, which has three regimes. There's this one, which is so-called early time physics, giving you a dip. There's a ramp, a thing that scales approximately linearly for quite a wide range, several decades in time usually. And then so-called plateau, where you get something that's time average, either time averages or ensemble averages to a constant. And the plateau is essentially a consequence of short range repulsion. It's a consequence of the nearest net of the smallest level spacing. And the linear regime is really, it's known as the ramp sometimes in spectral form factor. And that's really a consequence of the long range repulsion. So this gives you another way of organizing this data and another target to look for black holes in AdS.
So isn't the size of the height of the plateau just also determined by just random statistics, just by some random phase approximation? I mean, would you find it's e to the minus s just by some random phase approximation? Yeah, you would find it's of order, plotted this way, it would settle down to z of beta. Yeah, z of beta. Oh yeah, because you should divide by z of beta squared to normalize. So this is so you have two traces. I don't know. Should you divide by z of beta squared to normalize, or z of beta? If you divide by z of let's see. So at t equals 0, this is z squared. Good. And then it becomes z, right? So it's 1 over z down from its maximum value. That's right. Right. That sounds good. Yeah. Okay.
Hey, Kristan, I think the plateau value is z of 2 beta, right? I mean that. Oh,
thank you. Yes, thank you. Sorry. Yes. It's a order Z of beta for the purposes of that discussion. Thank you, Shuvik. That's right. It's Z of 2 beta in the random phase approximation. Okay. So the main claim of this talk is that the main claim, or the main thing I'm trying to discuss, is that the level statistics, not the density of states, but the level statistics of black hole microstates are encoded in Euclidean wormholes. And what I'm going to do, let's see, I need to speed up and maybe I can extract to 15 extra minutes or something for the end in order to get to the end. What I wanted to do
sure,
was
no problem for that.
Okay, sorry. So what I wanted to do was to first review how, that there's some precedent for this in low dimensional soluble models of gravity, in JT gravity, and there's some evidence in 3-dimensional gravity that this statement is true. I just wanted to review that evidence briefly. And then I wanted to go on to discuss wormhole amplitudes in higher dimensional AdS and in full-fledged AdS CFT, where we'll accrue some modest amount of a very, very modest amount of evidence that this is the case, but still building up to it. So what was known before? Well, this claim that I said there about the level statistics being related to microstates, to wormholes. This is true in JT gravity, and there's evidence for it in 3-dimensional gravity, pure 3D gravity with cosmological constant. So the statement in JT is due to a result of Saad, Shenker, and Stanford in 2019, and in 3D gravity, that's due to Jordan Kotler and myself in the paper that I mentioned from 2020. How does it work in JT? Well, one of the things that Saad, Shenker, Stanford established is that JT is a consistent theory of quantum gravity, and it's dual to a random matrix theory. A so-called double-scaled random matrix theory. And this is, in the same vein as the old 2D gravity story from the 90s. And well, from the 80s, I guess. And well, how does it work? Well, JT is a theory of 2-dimensional dilaton gravity. Its degrees of freedom are a dilaton and a metric. The dilaton effectively appears as a Lagrange multiplier if you give it the right contour. You integrate it out, it enforces a constant curvature constraint, and you have left over an integral over constant negative curvature metrics. And if you specify the topology of the surface, as well as the sizes of asymptotic circles, well, you can just do that integral over those constant curvature metrics. So for instance, if you consider the disk, that is, so hyperbolic disk, the disk with constant negative curvature, that disk amplitude, well, that can be computed exactly in JT. There's one parameter, which is effectively the size of the boundary circle that depends on beta. And the relation to random matrix theory is that this is equal to, well, random matrix theories have a genus expansion, an analog of a 1/n expansion. And this is the, within the matrix model, this is trace e to the minus beta h at genus 0, where h is the random matrix that one is sampling. And the angle brackets denote a matrix model average, meaning, you know, f of h is integral dh with respect to some distribution average over that, where h is an n by n Hermitian matrix. So that's what happens for the disk. And this, if you do an inverse Laplace transform, gives you the genus 0 approximation to the density of states. So that's how you can get a density of states from the disk. And if you consider higher genus things with a single boundary, say with boundary beta, with G holes, well, what does this compute? This computes trace E the minus beta H at genus G, which you can inverse Laplace transform to get a genus correction to the density of states. Of course, there's more, because in JT, you can consider the 2-boundary problem, or the 3-boundary problem, or the 4-boundary problem. And if you consider 2 boundaries, just for simplicity, say with nothing else in between, just a hyperbolic cylinder, well, this is the genus 0 approximation to the second moment of trace E the minus beta H. Where, since you have 2 factors of trace E the minus beta H, there's 2 betas, and those 2 betas are the sizes of the 2 boundary circles. And this is the thing that, after inverse Laplace transform, gives you 2-point function of density of states that has this universal form from random matrix theory, going roughly as -1 over E1 minus E2 squared. This is the long-range repulsion. It comes from this diagram in the bulk. And higher topologies, encode higher moments and further genus corrections to these observables, to endpoint functions of the density of states. And it's worth, I mean, we're kind of used to it now. Many of us are after a couple years, but this is, this really, you know, this is not only telling us that there's a duality between JT and random matrix theory, that these two things match so nicely, but it's also giving us a dictionary whereby we can interpret what is the dual of gravity with some number of boundaries that's not 1. How do we interpret it? Well, we interpret it as an endpoint function of the partition function. So for instance, if we have, you know, if we draw a picture, beta 1, beta 2, beta n, and we sum over geometries that fill these in all possible ways. Well, in JT at least, we understand this to be the partition function with beta 1, partition function beta 2, z of beta n. That's how we interpret the multi-boundary problem, as some endpoint function of partition functions.
So is there some issue about whether we can only be in the Euclidean signature, or whether these things also make sense in the Lorentzian signature?
Yeah, so what I just wrote, it's very Euclidean.
Right, so is there some understanding here? Yeah.
Yeah, I mean, how to say, you know, you could try, how to say, you can, by complexifying the betas, you could assign a Lorentzian interpretation. Oh, well, now you have, you know, time evolution operators, e to the minus I ht, instead of, you know, a Euclidean evolution. And you perhaps might like to interpret that in gravity in terms of some sum over Lorentzian geometries. But the way that the things are understood presently, I mean, what's really understood is the Euclidean dictionary, and Lorentzian is just obtained by continuation.
I see, but if one looks at, for instance, this Harlow and Jaffer's quantization of JT gravity, they would not reach these results, would they, if one just adopted their approach?
That's right. Well, what they get is, sorry, go ahead.
No, I was just asking if you had any comments on that.
Yeah, I mean, what they, how to say, my comment on it is that, the JT, unlike other examples of UV complete theories of gravity that we know, string theories, JT, you can make sense of the amplitude on any topology. Now, it's not that hard, actually. So for Harlow-Jafferis, they consider a two-sided black hole, and you can completely enumerate the space of metrics that you got to integrate over. You have boundary Schwarzian degrees of freedom. You have moduli. You can just you can construct the amplitude. And if you wanted to stop there, you could. That's a definition that you could make for that theory of gravity. You could adopt that attitude. That's the thing is that, how to say, if you do stop there, then, well, how to say, if you do stop there, if you don't consider higher topologies, at least in Euclidean signature, then you miss out on this connection with random matrix theory that persists to all orders in genus expansion. So yeah, unlike what usually happens, how to say, like in string theory, I don't know a good reason why, for instance, in the world sheet theory, we wouldn't just stop and consider summing over world sheets of a fixed genus and just let that be the end of it. We really have to sum over everything. In JT, it seems to be consistent to consider just a genus G amplitude and leave everything else alone. But if you do that, then you miss out on the duality.
Yeah, you might miss out on the duality, but you may not also have this factorization problem that you might reach later in the talk, right?
Yeah, I mean, yeah. That's true. How to say? So the question that you're getting at is I think really the central question for this whole business about wormholes. What is the integration contour in gravity? What really are you supposed to do? What are you really supposed to sum over these things? Are you not, or are you not? My perspective, maybe I can share my perspective on that question more broadly. I view this research program into looking at wormholes and their contributions and whatnot as very exploratory, as well, if we do include these things, what do we get? Rather than simply forbidding them from the outset.
Okay, thank you. Please continue.
Yeah. Okay. So that was JT. In pure 3D gravity, well, there's a very long story about whether pure 3D gravity exists as a consistent theory of quantum gravity in its own right, without any stringy degrees of freedom or extra dimensions or whatnot. There's reasons dating back into the past, say mostly due to Maloney, Whitten, and also Keller, that if you suppose that 3D gravity is a consistent theory of gravity, and you try to compute the torus partition function of whatever the dual is, that partition function is not that of unitary CFT. It has negative density of states. So they would say, well, that it's not a consistent theory for that reason. However, there's new evidence coming back from last year. So this is from us, from this paper of myself and Jordan Kotler, and then also Maxfield and Turiachi, that I would say we need to revisit that claim. In particular, when it comes to the density of states and whether or not it's unitary, the negative norm states that appear in the density of states written down by Maloney and Whitten, they appear near the spectral edge. And what Maxfield and Turiachi showed using a JT limit of 3D gravity is that if you sum over more complicated topologies than just something that has the topology of Euclidean BTZ or global AdS, if you sum over more complicated topologies, that those contributions are important near the spectral edge, and that they can give you a positive density of states, thereby healing the unitarity. So maybe that's not such a big problem after all. And then what Jordan and I did was to look at a wormhole amplitude in 3D gravity. And what we computed was sort of the simplest wormhole amplitude that you could, namely one where there's a torus on each boundary and just a bulk that smoothly interpolates between them. And so, if you will, the two tori are labeled by complex structures, tau1 and tau2. And so we got the torus times interval amplitude of 3D gravity, which depends on those two independent complex structures. This was the analog of the wormhole in JT gravity that gives you long-range repulsion. And what we found when we computed this, well, so how to say, it's a connected contribution to the two-boundary problem. We found that it's not zero, it's not infinity, you can make sense of it. It's some finite, well-defined amplitude, which strongly suggests that, how to say, what it suggests is that if 3D gravity is a consistent theory of gravity after all, that is, if it really makes sense, putting it on any three manifold and summing over topologies and so on, that the dual description is actually an ensemble rather than a single instance. You can get a factorization paradox, among other things. I should write down what the answer is for this because it's so pretty. If you're familiar with CFT partition functions or Maloney-Whitten or some such, you'll appreciate that it's very simple. In 1 over square root m tau1, eta tau1 complex square, where eta is Dedekind eta function. M tau2, Dedekind eta tau2 squared times sum over PSL to Z elements M tau1, M gamma tau2 over tau1 plus gamma tau2's complex square. So this is
Kristan, a question. So is there any constraint from unitarity on rho E1, E2? Like
okay, so from this you can extract a 2-point function of density of states. And are there constraints from unitarity on that? Yes, there are. They're the usual, I mean, how to say, this would be a contribution to the connected moment. And in the coincident limit, that connected moment has to be positive, has to be non-negative, just like the usual connected moments of probability distributions.
But nothing about integrality of, means there's no integrality.
No, you wouldn't, that's right. Well, especially if there's an average. Yeah, so this answer that you get, I write it down because it has the property that it, well, there's a sum in it. There's a modular sum, which if you're familiar with Maloney-Whitten, resembles the Maloney-Whitten modular sum. That's to do with the fact that you can sum over geometries where there's a relative modular transformation between one torus on one boundary and the other torus on the other. But the result is actually simultaneously modular invariant under independent modular transformations of both boundaries, of both boundary tori, even though there's a single modular sum. So this thing is quite constrained by symmetry. We had to work pretty hard to get it. There's evidence from some other viewpoints that it is really reliable. We have another work in progress with Brandon Rayon, which is computing this thing another way in second order formalism. Yeah, it's a nice answer. But what it gives you actually is you can extract the same eigenvalue repulsion from it if you look at the 2-point function that you extract from this of spin S primaries, which you do by some, well, you end up getting the same form for the eigenvalue repulsion, provided that the two spins are equal to each other, E1 minus E2 squared. So you get the same signature of eigenvalue repulsion. And in that, I mean, I'm not writing all the details of the expression down for the density of states. It's exactly the form that you would ansatz from random matrix theory with all the right symmetries to account for the fact that you're dealing with actually conformal field theory on the boundary. So it's quantitatively exactly the right formula. There's like factors of pi and square roots and so on that exactly work out. Right, so I say that, you know, so this is evidence for long range repulsion in AdS3 gravity. And I say evidence rather than, you know, a demonstration, because it's not yet clear that AdS3 gravity really exists as a consistent theory of gravity. That has yet to be shown. Its ultimate fate still hangs in the balance. There's evidence that maybe it's dual to some ensemble average, whatever that means to have an ensemble average of large central charge CFTs, but the jury's, we'll see what happens. This is what's known. And that brings us to the real meat of the talk. What about higher dimensional gravity? Honest to God, Einstein gravity in higher dimensions, or what even about string theory and AdS CFT? What about wormholes in that instance? And well, at this point, we should pause and note that these wormhole amplitudes that I discussed above in JT and AdS3, they're actually much more subtle than what I described. Like, to actually compute them, it's quite tricky. And the reason for this is that these are non-perturbatively suppressed. So they're like instanton contributions to in gravity, but they do not have a saddle point approximation. And in JT and in 3D gravity, you can get away with this because you can actually enumerate all the metrics that you're supposed to sum over, and you can really do the sum. It's quite miraculous that way. But of course, there's no chance there's no chance that we'll be able to do that in higher dimensions. So when we ask, well, what about finding wormholes in higher dimensions? How on earth are we going to do this? Well, how to say, you're going to end up with exactly the same kind of problems. And for this reason, you might want to give up and do something else with your life. But fortunately, it's not quite as bad as that. So yeah, there are similar problems in higher dimensions. For instance, there's something called the Whitten Yao Theorem, which states that if you look at Einstein gravity in, say, you know, in higher, you know, above 2 dimensions, then if the boundary is positive, if you consider just pure gravity where the boundary has positive curvature or is flat, and you don't turn on anything else, no matter fields, no nothing else, then there are no wormhole solutions of Einstein gravity with those boundary conditions. So there's no wormhole saddle that you could look for, maybe some non-trivial instanton of the gravitational field. It just doesn't exist. You can prove it doesn't exist. So, you know, if we're interested in something like we could call a wormhole that takes the same shape as what I wrote before, but where the boundaries have the same topology as a black hole in AdS, say thermal circle times spatial sphere, Well, there simply are no solutions to Einstein gravity of this sort, and we have to work harder. Again, if there's such an amplitude exists, it's going to be non-perturbatively suppressed, and it won't have a saddle point approximation because there's not solutions to the field equations of this sort. So we need new tools. And to be honest, I could probably give an extra talk or two just about the tools that we need to set up this problem. I'm just going to get started. So I can only give a brief overview of what the tools are that we use. There's one set of tools that we can use to discuss this problem that has a history in quantum field theory. There are instances in quantum field theory where you have similar physics, where there's instanton corrections to amplitudes, but where there's no instanton solutions to the field equations. One example of this is just Yang-Mills theory in a Higgs phase in 4 dimensions. In that case, the Higgs web obstructs an instanton that's solves the field equations. It's inconsistent with the Higgs web. Another example is super symmetric QCD, n equals 1 SQCD with n equals nf minus 1 colors. In that case, if you're out on the moduli space of that theory, well, it's kind of like what I just said, Yang-Mills in a Higgs phase. There's no instanton solutions to the field equations, but on general grounds, there are things that scale like instantons, corrections to amplitudes. And in both of those cases, there was a technology that was developed in the 80s to be able to handle that, called the method of constrained instantons. It was developed by Affleck in the context of, say, Yang-Mills in a Higgs phase, as well as Affleck. There's a lovely paper of Affleck, Dine, and Seiberg for n equals nf minus 1 SQCD. In either case, there's some methods in field theory where basically you slice up the integration over fields in a way. You introduce a constraint and you work at fixed value of the constraint, and then you integrate over the constraint at the end of the day, so that you just rejumbled around how you do the integral over all fields. And in that case, you can find new solutions to the constraint problem. Those are the constrained instantons. But then you have to integrate over the constraints. You end up integrating over a family of constrained instantons, and that allows you to get these corrections. And what you can do is you can adapt that method to Einstein gravity and find new configurations, new nearly saddles. So that's one way of finding these wormholes. And this is what we did in a paper last October. But what I want to do for this talk is actually a more refined, a somewhat nicer way that I'll call V2, which we gave it a name. We called these things Lambda Solutions. And let me describe what these things are. Okay. So what do I mean by a Lambda solution? Well, gravity is a gauge theory. We divide by diffeomorphisms. And so we have to gauge fix when we do anything, whether we look at the space of, the classical phase space, or we set up the one loop determinants, or what have you. We have to gauge fix. So suppose that we want to find geometries of this sort that I drew earlier, where a coordinate that goes along the wormhole from one side to the other, let's call it rho, and the other directions, let's call those xi. Something we can do is to gauge fix, we can pick a kind of radial gauge, or like Gaussian normal coordinates for a geometry like this. we can fix that the line element is d rho squared plus some residual metric gij x rho dxi dxj. So in other words, we can fix the rho component of the metric to be 1 and the mixed components rho I to be 0. And this is implemented in the path integral through an action that is the usual Einstein-Hilbert action. Plus a gauge fixing term, lambda mu times the gauge fixing condition, which if we wrote it out, it would look like that. And well, that's what we have to do. So in the gauge fix theory, the only degrees of freedom are gij. That's so if we integrate out lambda mu, only gij are the degrees of freedom of the actual gauge fix theory. Alternatively, if we don't integrate out lambda mu, we can think of those, they lead to an effective right-hand side for the Einstein's equations. Either way, leveraging this fact, we can find new configurations where, you know, if you keep track of what's going on, you can find a wormhole that's a solution to the equations of motion that's supported by the lambdas, by the gauge fixing degrees of freedom. So when we write these things down, we're really taking the sum over metrics, the path integral over metrics seriously and seeing where it leads us. This is a phenomenon that you would not anticipate in classical gravity, but if if we were doing gauge theory, this is just part of what happens, for instance, like when you compute the propagator in a gauge fix theory. These are sort of these are manipulations that you would do if you were looking at the propagator in in an axial gauge for QED or some such. You integrate out if you have a delta function gauge, you can just impose the gauge, and then you have a residual path integral over the remaining degrees of freedom, which often has the saddle point approximation for those residual degrees of freedom, the actual physical non-gauge fixed degrees of freedom. Or you can think of there being a combined like propagator or whatnot for your A mu as well as for the gauge fixing field. So either way, you end up with new solutions to the equations of motion of the gauge fix theory. And we call those things lambda solutions because there's a profile for the gauge fixing auxiliary field, which is like a Lagrange multiplier, which usually we denote Lagrange multipliers as lambdas. So for instance, if we talk about wormholes where you have a torus cross-section, like asymptotes between one torus on one boundary and torus on the other, we can find a whole family of metrics of that sort, where the line elements look like this. They look like, well, d rho squared plus parameter. We can find these in any dimension. They look like this. I mean, just to say, we can really write this thing out. So this is something that has the same kind of shape as what I wrote down before. There's a torus that gets really big at large negative rho. comes in, shrinks to some finite size, and then gets really big again as you go to very, very large positive rho. And the bottleneck of there has a size that is parametrically b to the d. So this, and why is there beta 1 and beta 2? Well, those are the sizes of the circle, which I'm denoting as tau, as it's like I'm separating out one coordinate from the others. So I want to make contact with black hole physics where the boundary geometry is, S1 times space. And I'm going to call that S1 Euclidean time tau. So beta 1 and beta 2 are the sizes of the tau circle asymptotically. And you have a geometry that interpolates from one side to the other. And there's really a family of these things labeled by this parameter b. And if you demand that the space-time is everywhere smooth, that puts a restriction that this b has to be positive, has to be, or rather non-negative. And it pinches off in the limit where b goes to 0.
B is same as lambda or it's different?
Right. The on-shell value of lambda is proportional to b to the d. Right. So that's with the torus. This you can check yourself if you compute the curvature of this thing. This solves all but the rho components of Einstein's equations, except in the gauge fixed theory, rho is not a degree of freedom. It's gauge fixed to 1. So that's okay.
And Kristan, can you tell us how exactly is this different from the constant instant-on method?
Well, the difference, if you will, the constrained instant-on thing, you can introduce, another way at arriving at this geometry is by hand to say, look, let me introduce a constraint which fixes the length of the geometry, the length between one boundary and the other to some value. And that also acts as an effective source on the right-hand side of Einstein's equations. You can get a geometry of this sort. And formally under the path integral, as long as you then integrate over all possible values of the length, you've done nothing. You've just reorganized the sum over fields. So, but at the classical level, as far as finding geometries, you get the same geometries. But when it comes to looking at the spectrum of fluctuations, computing one-loop determinants, things are quite different in those two cases. So here, we've gauge fixed a radial gauge. And so, for instance, if you look at this, if you've ever looked at fluctuations of Einstein gravity, all sorts of fluctuations will couple to each other. With the constrained instant-on thing, well, you added a constraint, but you haven't yet specified a gauge. So you could specify any of the standard gauges, like an RxI gauge or something, to kind of decouple as many degrees of freedom as you want. So things look the same, sort of at the level, oh, I found a wormhole geometry, but the way the amplitude is organized, spectrum of fluctuations, is a bit different.
Okay, thanks.
Right. So we also found it's actually quite tricky to find these wormholes. I mean, I'm writing down fairly simple ones, but in general, we can only find these things numerically. We found another example with an analytic wormhole with boundary S1 times S3 in AdS 5. There, if I write it out, it has kind of a qualitatively similar form. Humor me for a second. I just, so we can actually find the metric of these things. And in this case, it has the same kind of picture. There's a thermal circle with size beta 1 on one boundary. I guess the way I wrote it out here, this should be beta 2 at large negative rho, and this should be beta 1. So there's sizes beta 1, beta 2 of the two boundaries. And there's the parameter b controlling how big the bottleneck is. And in this case, non-singularity requires that b is bigger than or equal to 1 in these units. You get some value. A few comments about these wormholes.
Sorry, I have a question, Kristan. Sorry, I should have asked this a long time back. There's something that's worrying me, which is that in the Lorentzian signature, there should be a microcausality constraint, which is that an operator on one asymptotic boundary should commute with the operator on the other boundary. Is it obvious that in the presence of these wormholes that is not violated, maybe by an exponentially small amount?
Yeah. So if you continue to Lorentzian, this wormhole, these things admit a continuation to Euclidean signature. I spoke, sorry, I said that wrong. They admit a continuation to Lorentzian signature.
Right.
You can just take tau to I tau.
Yeah.
And when you do that, sorry, I'm just worrying about my earpieces going dead here. When you do that, the geometry that you get is a traversable wormhole.
It's a traversable wormhole.
It's a traversable wormhole.
But isn't that worrying? Because these two, I mean, there was no coupling you added between these two asymptotic geometries, right? So you have a geometry on one side and the other side. And
yeah. So, I mean, the thing is, this is, I mean, how to say, this is really, I would say that's really the Lorentzian avatar of the Euclidean factorization paradox. Like there's a problem in either signature. The problem in Euclidean signature is factorization, and the problem in Lorentzian signature is what you just described, non-commutation of operators on the two boundaries.
I see. So then, I mean, we can discuss this a little bit more later, but then isn't that evidence that one shouldn't ignore, well, one should not include these wormholes in the path integral? Because they're giving you something that's, you know, I mean, they're leading to a property of the theory that seems to be inconsistent.
One can adopt that attitude, yes. How to say I mean, I will have a little bit more to say at the very end. Again, this is the question: what is the contour of integration? What should one really sum over, and what should one not sum over? I admit, how to say, one can take, how to say, if one wants to forbid these things, I would like for there to be a better reason to do it other than by fiat. I would like for there to be some underlying reason within string theory why we should not include these. Whereas what I've seen, you know, the experience has taught us so far in very, you know, that usually we're supposed to how to say, like, let me enumerate a possibility, which is that, how to say, maybe in very broad terms, you could say, oh, maybe one can take a very democratic attitude toward summing over things, or a very totalitarian attitude, whether you're allowing more and more things or forbidding more and more things. And I tend to be sympathetic to the idea that one should include more and more things, and in particular, I would look for even more contributions beyond the wormholes that heal factorization and heal the things that you said.
I see. Okay.
Rather than forbidding these, yeah.
Okay, thank you.
But you know, that's metaphysics. We need at least calculations to be able to hold on to in order to even have those conversations. Right. So you get some family of wormholes. A few comments about these metrics. So one is that, well, I mean, all the ones I'm writing down, they're really at spin equals 0. So these are, if you will, like the you know, and we're used to black holes that rotate versus black holes that are non-rotating. These are like the non-rotating versions of wormholes. There are also rotating versions that we know much less about. We can study them sort of perturbatively in general dimension. We can study them in great detail in AdS3. But in higher dimension, we can only look at very, very small rotation. The ones that I wrote are non-spinning ones. So the analog of like a short shield, but for a wormhole. Another comment is that these geometries secretly are the analytic continuation of black holes. they're an analytic continuation of black holes, or maybe you could phrase it as the black hole being an analytic continuation of these geometries, but where you close off second region. The way to see this is that if you take beta 1 equals minus beta 2 equals beta, then these line elements are respectively the line element of Euclidean torus black hole and Euclidean black hole in global AdS 5, with a relation between B and the mass, where B to the D is roughly speaking the mass of the black hole. And so if you want to make the Euclidean, if you perform this continuation, the geometry pinches off at rho equals 0, which the thermal circle shrinks to 0 size if you stare like at this factor. And if, so that's a black hole background, and it's non-singular if and only if there's a relation between the size of the space of the sphere, the size of this B factor and beta. And that relation is the usual imposition of no conical deficit for a Euclidean black hole. But in any case, that you get, how to say, the wormhole is the analytic continuation of black hole, or vice versa, which I think is worth noting. The third comment to make is that the renormalized action, like if you do holographic renormalization and compute the action of these wormholes, it takes a very simple and appealing form. It's beta 1 plus beta 2 times the energy carried by the wormhole, the thing that you would get from looking at the boundary stress tensor. And that energy, it's the same energy on both boundaries. And it's parametrically B to the D times the volume of space over G Newton. So, this is a nice formula. In particular, it tells you that these geometries, if you compare it with the action of a corresponding black hole, it tells you that these geometries are always have higher action than a black hole with the same boundary data. And also that that the action is the action differences are very big. It goes as 1 over G Newton. And it also tells you that B is effectively fixing the energy that's carried by the geometry. Moreover, if this B is basically the energy, if you fix the parameter B, there's a completely well-defined loop expansion. You can look at one loop determinants around the background, a wormhole of fixed B. You can look at 2 loop effects and so on. There's a discussion there, what does fixed B really mean? That expansion exists. We could discuss that if you wanted to. But the punchline is that at fixed B, there exists a loop expansion. So this suggests a strategy for computing the whole sum over these wormholes, namely, you fix a B and then you work to some order in the loop expansion, and then you integrate over B at the very end with the right measure. And because B is this parameter B, the bottleneck size, it's geometric data, the right measure over B is determined just by the measure on the space of metrics that you're using to do the integral in the first place. So at the end of the day, this leads to an expression for the wormhole amplitude, which depends on the sizes of the 2 boundary circles. This is implicitly at spin equals 0, which is an integral over B, B greater than 0 for the torus, or B bigger than 1 for the S1 times S3. We can convert that to an integral over energies, where you start off at some minimum energy and go off to infinity. There's a Boltzmann factor coming from a classical gravity computation that's for normalized action. There's a 1 loop measure we could call f of E. And then there's 2 loop and higher effects. it's worth noting, it's a fun observation, this this regime of energies that you integrate over exactly coincides with the coarse-grained energies of non-rotating black holes in AdS. So for instance, for the black hole in global AdS, there's a range of energies for those black holes. Starting off with the small black hole threshold, which is the same as the vacuum actually in that case, and going off to infinity. This minimum energy is exactly the small black hole threshold in AdS. So you get some formal expression for the amplitude. We can get the classical Boltzmann kind of suppression. We can't get the one loop factor at this time. That's beyond us. And of course, two loops and so on is also beyond us. But, you know, okay, this is progress. This is something. In AdS3, or in JT, we can actually enumerate the loop corrections and actually do the integral. But in higher dimensional physics, well, we went from not having even a saddle point to having this. And, you know, you at least it's feasible, perhaps numerically, to make some estimates as to the one loop factor to try to estimate, well, how does this thing behave, at least for macroscopic wormholes, so for very, very large energies. However, there's a problem, and the problem is that this Boltzmann factor guarantees that the integral is dominated near the lower endpoint of integration in energies. In other words, the most important region of integration is as the energy goes to its lowest possible value, which in gravity corresponds to the limit where the wormhole pinches off to zero size. And that's the limit where bulk effective field theory breaks down, and this whole loop expansion at fixed energy or fixed B breaks down. So if you actually want the amplitude, that's UV sensitive. I'll have more to say about that a little bit later. We have a way to get around this now. We didn't back last October, but we have a way to get around this now. Maybe since it's late, I can just say, what I wanted to do next was to talk a little bit about a few other important physical questions like uplifting to AdS5 times S5 and stability and such. I'll do that in a moment. But regarding this point about extracting physics from this UV sensitive amplitude, basically what I'll say at the end is that we can take an integral transform of it. And we can extract that integral transform admits a saddle point approximation, where basically we integrate over beta 1 and beta 2. There's saddle point values for beta 1 and beta 2, and for the geometry, where the geometry is macroscopic. So the full amplitude is UV sensitive, but there is a certain integral transform of it, which is not. Okay, so but to summarize at this point, since it's getting late, at this point, what do we have? We have a way to analyze, or to maybe parametrize is a better way of putting it, certain connected contributions to the two-boundary problem in Einstein gravity. Per the discussion with Subrat, assuming that we should actually do this. So in other words, you know, if we have two boundaries and we try to sum over everything, well, that has a disconnected part plus a connected part, where at least the simplest topology to write down is this, what we're doing, plus, you know, ... other connected contributions or non-geometric things or what have you. So at this point, there are three things left to address before wrapping up. The first one is, well, what I just described was within just, Einstein gravity with negative cosmological constant. You should ask, what about full-fledged AdS CFT? So for instance, what about uplifting to AdS 5 times S5? Another question that we can ask at this point is, what about stability of these geometries against perturbative effects as well as brane, non-perturbative nucleation processes once we embed these into string theory? And the third question is this thing of extracting reliable physics from the amplitude. Meaning physics that can be analyzed in bulk effective field theory. And I'll comment on each of these in turn. So we have positive answers to all of these questions.
Kristan,
So for the first one,
about the
yeah, go ahead.
Yeah, about the Z beta 1 beta 2 expression that you wrote down. So
yeah.
means, do you know how this f of e grows, or the
How what? Sorry.
How the f of e that you wrote down in the right hand side? So it does not grow very fast. Is that what you were saying, or?
Yeah. It's if you express it in terms of B, it's just a one loop factor. So, G doesn't appear in there. It appears as some overall homogeneous factor times some function of B. Yeah. And then if you express B in terms of the energy, then it's a very, very slowly varying function in the energy.
But you still mentioned that there is some integral transform where you can analyze this thing.
Yeah, so, basically, roughly, this thing is naturally, okay. I guess we can talk about it now. We can do 3. So what is the integral transform? Well, this amplitude is naturally, you can think of it as a canonical ensemble quantity, since it depends on betas, not energies. But you can ask, what about is there a microcanonical version of it? Where you fix the energies instead of betas. And to go from canonical to microcanonical, well, that's an integral transform. That's inverse Laplace transform. And that, it turns out, is dicey. That's a little sensitive. However, if we look at a microcanonical version with a resolution window, we're used to this in statistical physics, where you fix the energy up to some bin of size, some resolution that you can call delta. Well, in that case, okay, so say we fix the two energies to be the same. We have a resolution window, and I'm going to introduce another parameter, t. How do we do this? Well, we integrate the betas, the sort of thing that we would do in an inverse Laplace transform. We integrate over a contour parallel to the imaginary axis. And what do we do? Well, we integrate with a Gaussian filter. So if it was just without the delta, without the resolution window, it would just be Fourier transform. But with the Gaussian filter, it's this plus delta squared beta 1 squared plus beta 2 squared over 2 times the wormhole amplitude at, well, now it's convenient to make an analytic continuation like this for reasons that I could explain if we have a little bit more time. If you take the wormhole amplitude and you make the continuation appropriate to consider the spectral form factor, you introduce a time t. Well, the net output of this Gaussian integral, you now have all the stuff that goes into the wormhole amplitude. In particular, there's the integral over energies that's implicit there. And then there's also the integral over beta 1, beta 2. And what happens is that this combined integral, just thanks to the Boltzmann weight in here, that there's an integral, we could call it dE prime e to the minus beta 1 plus beta 2 e prime. Well, times stuff that's slowly varying. Well, this is basically the slowly varying stuff you can ignore at leading order in the saddle point approximation. This is just a Gaussian integral in beta 1, beta 2. And then that leads to a Gaussian integral over E prime after you follow everything through. And all of those things, it turns out, have good semi-classical approximations, as long as you take the resolution window to be small, but not too small. In which case, there's saddle point values for everything in sight. And you have something that's, you basically extract a geometry with a fixed metric, except the saddle point that you land on is not a Euclidean geometry. The saddle point that you get, so the ensuing saddle is the double cone geometry of the first Saad, Shenker, Stanford paper. From 2018. So this is a geometry that's a time-like orbifold of two-sided AdS Schwarzschild. But you get it, it wasn't clear, I would say. There were, the status of that geometry, well, it wasn't clear what one should do with it in AdS gravity. And one of the things that this project answers is, well, you can really land on that geometry by a principled computation in Euclidean gravity.
Sorry, but what is this parameter delta? How do you interpret it?
Yeah, so the delta parameter, you're right. So maybe it's easiest to say what this thing corresponds to. Like if you associated it with an ensemble average, what it corresponds to. What it would correspond to is a trace e to the minus h minus e squared over 2 delta squared. So it's giving you like a contribution to this. So you, instead of looking at the density of states per se, it's some fixed energy, like a microcanonical version of spectral form factor. What you do is you smear it a little bit over a width delta. Okay, so that's what delta is. What is it in gravity? Delta is something that is insensitive in class. It doesn't appear in classical gravity. It appears at one loop. And when I say one loop, I mean at the level of one loop fluctuations, both of the metric degrees of freedom as well as of beta 1, beta 2, since we're integrating over those. Right.
So Kristan, can you read off the, I mean, can you read off some information about the eigen energy statistics, like with whether they repel each other or anything?
Yeah. Right. This? That's where we started, right? So okay, so we can't, so this thing, if you take the long range repulsion answers, at face value, you would expect this to go, the signature of repulsion in this case is that this has some functional dependence on the energy, but that it's approximately linear in time, or at least that this is the contribution, this is the ramp, if you will. That's what it corresponds to here. I'm sorry for being very schematic. I haven't actually I don't actually have this equation written down in front of me, but the ramp in the spectral form factor manifests itself as a linear in time contribution to this 2-point function, this sort of microcanonical version of spectral form factor. But there's a particular form for the function of energy out front that you would expect to be multiplying it, that you can get from, if you will, from like random matrix theory expectations. And well, in gravity, what we can see from here is that we can basically see the linear in time factor arise. That's a one loop effect. Basically, the rise is from the double cone because you can relatively twist one boundary to the other, and that's an exact zero mode of the geometry. This twist. And the zero mode field range is parametrically order the size of the circle, order t. However, the function in front of it, its dependence on the energy, depends on one loop fluctuations. Which and analytically you can do, and that's beyond us now. There's some hope that there's some hope that maybe in sort of a low temperature, late time regime or something, that you could maybe you could try to estimate the determinant in terms of these. It comes from these one loop determinants, and maybe you can estimate those from the lowest energy states, the lowest eigenvalues, which are amenable to numerical analysis. But we can see the linear in time scaling very clearly.
So in the pair correlation function of the spectral densities, so due to this T present, I imagine there will be a 1 over energy difference squared, but you have some additional dependence through this f of E. So it's a.
That's right. That's right. And also there's the time evolution. I mean, if you didn't have the time evolution, you would expect a linear in time, and there would be no thing in energy. And if you didn't have the time, then you would expect, the repulsion. I forget how this looks like, but you can get it out of say, you can just get it from I mean, if you wanted to compute this in random matrix theory, you just replace these traces with rho of E times the appropriate function of E, and then you can yeah. Okay, sorry. When I talk for too long, the screen shuts down. Anyway, okay, so the other two comments, what about uplifting to AdS5 times S5, say, or other lamppost examples of AdS CFT? We can do that too. Let me comment on that briefly. So how does that work? Well, let's talk about AdS5 times S5 for concreteness. Well, in that case, the place to start is with the 10-dimensional Einstein frame metric for type 2D supergravity. And that 10-dimensional Einstein frame metric, we can write it this way. It's conventional to write it out in terms of, for people that do KK physics, they're well used to this, where the 5D metric is not just, it's not obtained from just the 5D components of the 10-dimensional metric. There's a Weyl shift sitting in front of it, a Weyl shift by the S5 warp factor. So there's the 5-sphere part, and then there's the 5D part, and there's that conventional Weyl factor there. And why is that conventionally there? I mean, it's a field redefinition, so you can put it there or not put it there. What's the reason why you put it there? You put it there so that the 5D metric is an Einstein frame. So this G5, this is the 5D Einstein frame metric that you would get in AdS5. And phi is effectively, if you consider fields that are S wave on the S5, phi here, the S5 warp factor, is a massive scalar. It's just a minimally coupled scalar of some mass, and its minimum of its potential is at phi equals 0. So the S5 is just at fixed size 1. Well, we can find a wormhole in this case, a 10D wormhole geometry, which is just of the form ds squared wormhole in the 5 directions of AdS plus d omega 5 squared through this lambda solution thing that I described earlier, provided that we make a gauge fixing whereby the mixed rho sphere components of the metric are set to 0, and where we also set the 5D metric components rho mu equal to delta rho mu. So in other words, we gauge fix the 5D metric in the same way as above, and we gauge fix that there's no mixing between rho and the angles on the S5, and those things combined will allow us to easily uplift our wormhole to a solution of the gauge fix 10D supergravity. I mean, it's a little bit harder than this because you also have to figure out the Ramon background, but that's basically fixed by flux quantization. So it's this plus a flux background. So you can find the wormhole this way, and you can also do similar things in AdS4 times S7, AdS, all the usual examples. The last comment.
Is it clear that that solution dominates the two-point function?
It has an action that is suppressed relative to black holes with the same boundary topology.
But I mean, as a wormhole, couldn't there be like other wormhole solution?
That it's the most important wormhole? No, we have no proof that this is true.
Okay.
Yeah. I mean, it's akin to asking if, I mean, there's a famous problem along these lines in gauge theories. There's instantons that we all know about. There is evidence from the perturbative, from the growth of Feynman diagrams that there are renormalons in gauge theory, configurations that would be non-perturbative corrections to instanton-like configurations, but with an action 1/n times that of an instanton anti-instanton pair, and we've never found those in flat space gauge theory. So in infinite volume gauge theory. So it's like finding configurations that are more important than an instanton. Usually, if you haven't found them, then there's not much you can say about them.
Yeah.
Okay, so last comment, stability, and then I promise I'm done. Hopefully it's been a fun discussion. I've enjoyed it. We've undertaken an analysis of stability of these wormholes, and as far as the perturbative stability goes, well, that's hard actually. That's a little tricky, and it comes with a problem that that no one can answer, which is this problem of the conformal mode of the metric. How does one actually define the integration contour over fluctuations of the conformal mode? So it's difficult, especially on account of conformal mode. And the problem here is that unlike in pure vacuum AdS or a solution to an Einstein manifold, the conformal mode actually mixes with other metric components. So the stability problem is quite subtle. What we've been able to do is, if we continue in the usual way, the standard thing that people do with the conformal mode is they rotate its contour. If we do that, then we find that the torus wormholes, we can just prove that they're stable in any AdS. So torus wormholes are perturbatively stable with that prescription. And as far as S1 times S3, what we can show is that that one becomes a little bit trickier. What we can show is basically that there's no level crossing. That we can show that it's stable as well as a configuration in 5 dimensions with this assumption again, because we can show that there's basically the S1 times S3 wormhole asymptotes to the torus wormhole when it gets really big. And what we can show is that as you shrink the size of the bottleneck smaller and smaller and smaller, that no eigenmodes of the determinant cross through 0, that there's no level crossing, and that would indicate a perturbative instability. So the S1 times S3 wormholes are also stable in AdS5. That's with this prescription. And within 10D, we can do some, this is also true when we uplift to 10D. So it's, right. So, and then there's a discussion with non-perturbative instabilities as well with branes, but I'm horrendously over time, so I had better stop now. Thank you all very, very much for your attention.
Yes, great. Thanks for the great talk. Yeah, if Kristan is not too tired, maybe we can have a few more questions. Anyone?
I have a question. Am I audible?
Yeah,
Hello.
sure.
Hi. So did you also have constructions for multiple boundary configurations?
No, we have not been able to find configurations with more than 2 boundaries.
Okay. And I have one more question. So
Yeah.
recently Stanford had this model where like it's some 0-dimensional system, and he could argue that like there are 2 ways to do the problem, where one in which you can include wormholes, and
Right.
other in which there are no wormholes, and he could show that there is a resolution of the factorization problem where you could look at the wormhole and the limit of where the wormhole is turned off, and that factorizes, and the sum of those factorizes. Did you have a comment? I mean,
Yeah, I mean, how to say, this is sort of along the lines morally of what, this exchange with Suvat earlier, and what happens in that case so there's 2 things considered, if I remember correctly, in that paper. There's a 0 plus 0 example, and then there's also some stuff with SYK. I admit I don't really understand the discussion with SYK because I mean I can explain, but basically there's some prescription there, but it's speculative, and I don't understand what the prescription is at loop level. But in the 0 plus 0, that's sort of along the lines of what I was hinting at in the discussion with Suvat. There, if you will, you have the wormholes, but you have other geometries, you have other configurations as well. And it's really the sum over all of them that you can think of as restoring factorization.
Okay.
So whether or not that's what happens here or not, I mean, it's a nice example. It's hopefully illustrative, but there's a lot to do. I'd say it's far from clear that that's actually what happens in gravity.
Yeah, I just asked because the way we also proceeded here like sounded very similar to that in the sense that you have an alternate discussion where you can introduce wormholes by introducing these gauge fixing parameters, and it seems you can also switch in that theory you can take the limit where the wormhole goes away, and it seemed like so the way Stanford phrased his result, like there's an identity which related these 2 theories, right? Which is that the wormhole plus the limit of where the wormhole goes down factorizes. So it seemed like this setup seemed like very right to check that. Yeah, thanks.
Yeah, I mean, whether or not there's a similar identity in full-fledged gravity, I mean, one would like that to be true, but I admit I don't quite see how I could get it from the gauge fixing apparatus. I mean, what the gauge fixing apparatus would tell me is that if I change if I'm careful and I do the Faddeev pop-off procedure and I include ghosts and so on, that no matter what gauge I pick, I better get the same answer for it. I'm not sure how I could go from that to an identity like that one. If one could, that would be very interesting. I admit I don't see how yet.
And I had another question that is when you wanted to get to the single geometry limit, we had to fix the beta of one of the boundaries to be negative.
Yes, yeah.
Right. but it also seemed to me that in the double partition function, if you have a negative beta, you might have a problem
Oh
at
yeah,
the
no,
large
that's quite
D limit.
that's
right?
quite bad. Yeah. This is it's a comment. It's an observation about the geometry. It's something, you know, it's striking that these geometries are related to each other. I would say it's striking that they're related to each other by continuation. It's an observation I would say is worth recording. My gut feeling is that it means something, but I don't, you know, scientifically, all I can say is it's an observation.
Couldn't you get many wormhole solutions using this?
Well, you know, it's how to say, you know, analytic continuation is an art, right? You know, in principle, yeah, it seems like one should be able to get, you know, for instance, spinning wormholes this way. In practice, okay, maybe we're just bad at it. We haven't been able to get to do it yet.
I see.
Somehow these Gaussian normal coordinates are they make the continuation manifest, and the problem is that, for instance, spinning wormholes do not, spinning black holes even, they do not have an analytic expression in this kind of coordinates. So so continuing to the wormhole is you know, we can't even get the black hole, let alone the wormhole.
And so what about getting like supersymmetric wormholes in AdS 5 times 5?
Right. So, well, okay, so the configurations that I'm writing down break all supersymmetry. They have to. They have energies above the BPS bound. Are there configurations, wormholes that preserve supersymmetry after some twisting? This is a question that I actually just had with someone earlier today. I don't know. So for instance, you might wonder how to say that there's work that other people have done that I am less familiar with about the superconformal index. You know, I'm familiar with the old papers about the index of n = 4, but there's recent work suggesting that that there are actually black holes that contribute to the index when you compute it in AdS, supersymmetric black holes. And you might wonder if, you know, if like in the index, there's an effective Hamiltonian, and if that Hamiltonian is chaotic, then all the same words from the beginning of this talk would apply. You might expect there to be level repulsion in the spectrum of that Hamiltonian. And you might wonder if there's if there's wormholes, supersymmetric wormholes, with the appropriate twisted boundary conditions corresponding to the fact that you'd be studying the index rather than the thermal partition function. But I have nothing more to say other than it sounds like an interesting problem.
So Kristan, just a general question. So means if you carried out the same thing in other some general gauge theories, this lambda kind of Lagrange multiplier analysis, then one can still calculate this rho E1, E2. And can one in general theories, can one still get is there any characterization beyond wormholes for arbitrary gauge theories which will say whether a theory will have such saddles?
Whether there'll be what, sorry? Pardon?
One can imagine some other characterization for more generic gauge theories which will say whether the theory will have such RMT like saddles. Is it even possible that there will be
maybe can I interpret your question as asking whether or not these configurations would lead to new instanton like effects in gauge theories?
Yes, roughly.
This is something we're trying to chase down, actually. It seems like it should, but how to say, if we are in Maxwell theory, then there's no new saddles that you get this way. You can find new solutions this way, but they violate boundary conditions, unlike these wormholes. So the interesting thing to look at is Yang-Mills, and the thing is that somehow like the Yang-Mills equations are usually as nasty to solve as the Einstein field equations, but somehow the wormhole equations have actually been much, well, the Einstein's equations have been much kinder to us than Yang-Mills for that problem. So work in progress.
Yeah, and then is there anything why things are dimensionally independent, at least the on-shell action or this?
Yeah, this beta 1 plus beta 2e. So there's a result in GR that if you have a geometry with a U1 isometry, that the action has to be beta e.
Okay.
Just because, you know, if there's a circle and it has some finite size, and you get around that for the black hole because the circle shrinks to 0 size, which leads to an extra constraint. But for the wormhole, you know, there's an isometry at play because you can rotate around the circle, and if you think about it a little bit further, even though there's two different betas, that's enough to tell you actually along similar logic that, oh, for just a normal thing, it had to be beta e, that it actually has to be beta 1 plus beta 2e, where e is the boundary energy. So that's why it assumes this very simple form. The fact that the energy is b to the d over g Newton, that's a more refined I mean, it's not a very refined computation, but that's an actual computation.
But also the RMT expectations are independent of dimension, which you were saying.
Yeah, well, that goes back to the discussion with Loga. That's kind of a, yeah. That's right.
Thanks.
Any more questions? I guess it's also getting pretty late for you, Kristan. Just I had maybe a little question, if you can comment on it. So actually following up on a question by Akhil. So you showed that in 3D, you can get the answer for the wormhole using modular bootstrap.
Yeah, that's right. I didn't talk about that at all today, but yes, that's right.
Yeah, and I was wondering, like, couldn't you also get like the multi-boundary answer, like in the same way? Or?
Well, so the thing that, okay, so we had this way of getting the torus times interval amplitude from a bootstrap. And the way that we were able to get away with, to be able to do this was the fact that, okay, so here's this whole answer. This whole thing you can write as a modular sum of something that we called a pre-amplitude, which is what you would have gotten. It's like the analog of the vacuum. What vacuum character is to Maloney-Whitten partition function is this pre-amplitude to the full amplitude. And the pre-amplitude comes from sort of what you naively get from this torus times interval, but before doing all the twists of one boundary to the other. And this pre-amplitude has a property that generic amplitudes in AdS3 do not, which is it's not modular invariant, but under independent transformations, but it is independent under invariant under simultaneous transformations of the two boundaries. So in other words, this z tilde gamma tau 1, gamma inverse tau 2 is z tilde the pre-amplitude. So if you do kind of diagonal transformations, then this thing is invariant. And that was really the beating heart of the bootstrap derivation. Like this combined with other phenomenological inputs from 3D gravity basically uniquely pins down the answer for what this thing has to be. And that is generically not true for multi-boundary amplitudes in AdS3. So it would usually, if you drew something with like, I don't know, like a genus 2 surface over here, interpolating to, I don't know, genus 1 surface over here, and maybe another genus 1 surface over here. Well, in this case, there's no like simultaneous, there's no invariance here. of this amplitude before having a bunch of modular sums coming from relative transformations of one boundary to the other. So there's no analog of this for generic multi-boundary amplitudes. So in general, no, I don't see it being possible to use a bootstrap to constrain these. The one exception is if you have higher genus surface on one boundary and same thing on the other. Then in that case, that amplitude, there's going to be a pre-amplitude, which is invariant under like a diagonal mapping class group, the analog of SL2Z, but for higher genus surface.
I see. But in the multi-boundary case, it's still the final answer is modular invariant independently on each parameter, right? So,
that's right.
But
But
this is not enough.
In general, it's kind of automatic because it's like Maloney-Whitten. Yes, the answer is modular invariant because you summed over all the modular images. That's not the modular invariance is automatic then. Whereas for these particular amplitudes, there's a diagonal part of it that is manifest from the bulk.
Okay. Okay, great, thanks. Any other question? Yeah, I guess maybe we should leave you go to sleep now.
Yeah, thank you so much. My apologies again for going on. Hopefully this was useful and fun.